Right. So the final problem we want to prove NP complete is the TSP problem, one you're familiar with. The reduction is going to be from Hamiltonian cycle, which we've just proved NP complete. So as a reminder, the input to the TSP problem is a complete undirected graph. Recall that a complete graph is one where you have an edge between every pair of vertices. In addition, each edge has a weight associated with it. And the question is there a tour, a cycle that hits all of the vertices, of cost less than or equal to k, where k is a parameter to the problem, right? This is the decision version of the problem. In the optimization version, you're trying to minimize, you're trying to find a tour of minimum cost. So I'll demonstrate the reduction from Hamiltonian cycle with an example in a little bit, but just as a quick preview. So we're going to need to create a new TSP graph from the original Hamiltonian cycle graph. There are going to be a couple of key differences. So the Hamiltonian cycle graph, firstly, is not complete, and secondly, it's not weighted. All right, so that's why we're going to need a different graph for TSP. So what we do is you start in the TSP graph with exactly the same set of vertices as you had in the Hamiltonian cycle graph. And then you have an edge between every pair of vertices. Edges that were in the HC graph now have cost 0 in the TSP, and the edges that were absent in the Hamiltonian cycle graph become edges of cost 1. So why don't I switch to an example. Okay, right here. So very quickly, in the example on the left, you'll agree that it does have a Hamiltonian cycle. And hopefully you'll agree that the example on the right, so again, just to be clear, so this is the example on the left, right? This has an obvious Hamiltonian cycle in it, right? And the example on the right does not have a Hamiltonian cycle, okay? So we already know that. Now, let me go ahead and erase these. So in both cases, our TSP graph is going to look like the one I've drawn at the bottom, right? So both of my Hamiltonian cycle examples had 4 vertices. And so I copied the 4 vertices over, and in the graph at the bottom there, I have an edge between every pair of vertices as is needed for the TSP problem. Okay, so focusing on the reduction from the graph on the left, all we really need to do is to add cost values. And the way we do this is when there is an edge in the Hamiltonian cycle graph, so meaning for these 4 edges, we add a cost of 0. Okay, so we're giving these edges costs of 0. Right. And see, I lost one of my zeros here. Okay, and then there are the 2 new diagonal edges, and so we will give them costs of 1. Okay, so that's 1, and that's the other. Okay, and so this is now my new graph. And the question now is there a tour of cost 0? Right? And you'll see that the only way I can get a tour of cost 0 in the TSP problem at the bottom is if I had a Hamiltonian cycle in the original graph, right? So, so in fact, my tour here would look like this. right? Which is exactly the Hamiltonian cycle in the original graph. Okay. Now, let's consider the second example. So I'm going to eliminate all of my costs here. Remember, the appearance of the graph is the same because my graph on the right also had 4 vertices. Okay, so we're now doing the reduction in this direction, focusing on the cost values. And so wherever I have an edge, I have a cost of 0. So I have a 0 here, a 0 here, 0 here, and then 1 on the diagonal right here. Okay. And so what that leaves me is 2 edges with 1s on them. So one of these is the edge on top, the horizontal edge on top, and then the other one is the diagonal that is sort of going from southwest to northeast. And let me try to squeeze in a 1 there as well. Okay. And now it should be clear that it's going to be impossible to find a tour of length 0 in this weighted graph, and that's because the original graph didn't have a Hamiltonian cycle. Okay, so that's the outline of the proof of NP completeness. With this, we are done with the chapter on NP completeness.